Welcome back, everybody. Today we will be talking about functions of random variables. So this is the last thing that we did was combinations, permutation, and also the properties of probability. So this one is going to tie into what we did a while back with the binomial expansion. So hopefully you were able to watch that video or have some sort of recollection of what we did then. So here's an example problem of what what I'm talking about. So for any one free throw, you have a 70% chance of making the basket. You are given 4 free throws. What is the most probable number of baskets you will make? Also, what is the chance of you making at least 2 free throws? So what we'll do first is we'll think of this as a function. Okay, so we're going to go ahead and write the following. I'm going to go ahead and say that p of x. Okay, so let's go ahead and do this. Let's say let p of x represent the probability of you making exactly x number of free throws. Okay, so what we're looking at is going to be a function. And so for the situation here, we're going to limit x then, because x, since you are only given 4 free throws, then that means that x can only be equal to either 0, 1, 2, 3, or 4 then. Okay. So now we're going to go ahead and try to solve for each one of these and see what happens. So we'll start by first solving for what is p of 0. Now remember, keep in mind p of 0 then tells me what is the probability of you making exactly 0 free throws then. So to me, that tells me that you're going to miss every single one of them. The probability of you making any free throw, according to what we just said earlier, is supposed to be 70%. So the probability of not making a free throw is going to be equal to the negation of that, which is 30%. And in this case, that's going to be the way that we're going to get this answer. So it's going to be 0.3 multiplied by 0.3 multiplied by 0.3 multiplied by 0.3. Basically, the same number raised to the 4th power, because we're going to miss every single one of those. So taking that, we can go ahead and plug that into calculator quickly to solve for that. So that's 0.3 raised to the power 4, and that gives us approximately 0.0081 then, so 0.0081. Now let's look at the next one, the probability of making exactly 1 free throw. So that tells me that you're going to miss 3 and you're going to get 1 of them. So this right here, just kind of like writing on the side. So we're going to have 3 miss and 1 free throw, 1 throw. So that is in the same manner going to be 0.3, but this time raised to the 3rd power. And you also have 0.7, and I'm going to raise that to the 1st power, because remember, you're going to get 1 free throw. Now, out of the 4 free throws, you can technically make that free throw out of any one of the 4. So that in itself is going to be a combination setup. So to be a little bit more specific, it's going to be 4C1, because again, out of the 4 free throws, you're creating 1 of the free throws. So that is going to be 4C1 over here. Okay, so let's go ahead and take that and put it into the calculator. So we have 0.3 raised to the 3rd power, and then we have 0.7 raised to the 1st power, and we have 4C1. So this looks like is going to give us 0.0756 then. Okay. Now we'll go down the list and solve for the next one. The probability of making exactly 2 free throw and missing the other 2. So in the same manner that I'm seeing 4C2 multiplied by 0.7 raised to the 2nd power times 0.3 raised to the 2nd power. So putting that again into the calculator, where this is going to be a 2 and this is going to be a 2. The answer for this one is going to be 0.2646. So it's approximately 26% in this case then. Couple more things to go and then we're pretty much done. So probability of 3 free throws and exactly 4 free throws. So next one is going to be 4C3. That's going to be 0.7 raised to the 3rd and 0.3 raised to the 1st. And that, if I put it into calculator, so let's see, 0.3, so let's see, 3 over here, 1 over here, and 1 over here. that is going to give us 0.4116 then. And for the last one, you're going to have all four of the shots, you get them. So that's going to be 0.7 raised to the fourth power. And, if you want to go by the pattern that we have right here, you technically can write it as the following. 0.3 raised to the 0 power and 4C0. Now, those are each equal to 1, and that's the reason why we don't normally write it. But, if you want to see it that way, that totally works too. So looking at our last one, let's see, 0.7 raised to the fourth, and then this is to the 0, and this is to the 0. This is going to give us point, and this is, 2401. Okay, so there it is. So those are all the possible scenarios out there, and if you add them all up, the answer should equal to 1 because, well, you can't have any other scenario. You can look at it algebraically, numerically, it's all going to add up to be 1. So hopefully that part makes sense to you because, again, those are all the cases. Now, what we can do with this is we can also kind of graph it out to see what's happening. So here underneath, this is going to look like the following here then. Let's say that this is going to be x down here, the number of free throws that you're going to make, and this is going to be p of x, which is the probability of that free throw happening. So let's see, at 0, you are going to have a probability of 0.0081, so that's going to be a very small number. So probably somewhere, like down here or so. Okay, so that's going to be 0. Now at 1, you are going to have 0.07, so about 7% chance. So assuming that, there's like 10%, 20%, 30%, and 40% scaling according to the numbers that we have. Number 1 would then be over here then at 7%. At x equals to 2, then we have about 26%. So we're going to go up higher to somewhere around here. Okay. And then at 3, we are now going to hit 41%. And I think that's going to be our answer for one of the questions because I want to find out what is the most probable number of free throws that you're going to make. So let me go ahead and isolate that as an answer. This guy right here is going to be the most probable. Okay, so that we have one answer. Most likely to occur. Okay. And finally, for the last one, for the sake of graphing, is going to be 4. The chances of you making exactly 4 free throws, and that is going to be around 24%, so it's going to be a little bit lower then. So these are the points that makes up the curve for this probability. And be very careful about how you sketch this curve. You're technically not supposed to connect them because you can't make half of a free throw or a quarter of a free throw. So that means that this is going to be kind of like a perforated curve then. So this is what it looks like then. So this is what is known as the binomial distribution for the probability. If you're wondering, well, where does the binomial distribution part comes in? Well, what I want you to do is notice that the middle part over here, hey, this is actually the binomial expansion. Okay, this, if you were to write it out, if you sum up all of it together, the question is, well, why is it equal to 1? If you were to write this out as a binomial expansion, this is going to say the following. It's 0.3 raised to the fourth, and then plus the first one, 4C1. Now, the way we denoted earlier or in the past was it's going to be 4 choose 1, right? And then we have 0.3 raised to the third power, and then we have 0.7 raised to the first. And then plus the next one, 4 choose 2, and that's going to be 0.3 raised to the second, 0.7 raised to the second. Then we also have plus the next one, which is going to be 4 choose 3. So that's 0.3 raised to the third. Not raised to the third, raised to the first in this case. So let me go ahead and erase that quickly. Whoa, we erased way too much over there. So I apologize for that. So let's see, plus, let's see, this is supposed to be 4 choose 2. And then this guy is supposed to be 0.3 raised to the first. And then we have 0.7 raised to the third. And then the last one, which is going to be 4 choose 0, if you want to write that out. So that's going to be 0.3 raised to the 0, and then times 0.7 raised to the fourth. Now, supposedly, when you add them all up, that's supposed to be our answer, which is equal to 1. Well, if you're using the binomial expansion, this is the same thing as saying 0.3 plus 0.7 raised to the fourth power, going back to that section. And what's 0.3 plus 0.7? Well, that's equal to 1. So that's another way to show that, yeah, the sum should equal to 1 then in this case. Okay. The final answer that we also want to get out of this is also what is the chance of you making at least two free throws? So for this part right here, if I'm going to make at least two free throws, we are looking at P of x that is greater than or equal to 2. So that means that's everything from 2 all the way to 4 over here. So the best way to do that is basically to isolate those terms and add them all up. So in short, I want to have P of x of greater than or equal to 2. That's equal to P of 2, exact probability of making exactly 2 free throws, plus probability of making exactly 3, and then plus the probability of making exactly 4. And if you add them all up, that should be your answer in this case then. So let me just kind of quickly do that for you. So 0.2646, and then plus 0.4116, and then plus 0.2401. So the answer is pretty good. Looks like it's about 91.63% then. Okay, so there you are. All right. So hopefully that example was explained thoroughly enough that you understand what's happening there. Now what I want to do is I want to look at another scenario of the probability that we've been working with, and you apply it to something that is a little bit more common. Okay, in this case, what I want to look at is what is the probability that you will be dealt exactly two pairs in a poker hand. So we're changing gears. We're no longer looking at the binomial distribution thing. We're just looking at a probability problem that we deals with combination and permutation, and stuff that we've been doing so far. So to first explain what this means, first of all, when I say a poker hand, that means that in a 52 card deck, you are dealt 5 cards. So algebraically or numerically, what that means is we have a combination situation, right? We have more specifically 52C5 because out of the 52 cards that you have, you're going to be dealt 5 cards where the order doesn't matter, and you're going to use those 5 cards to create your poker hand. That right there is going to be our denominator then, because that's the total number of events that you can possibly have. In our case, I want to look at what's the probability of having exactly 2 pairs. So I need to look at all of those scenarios and then try to figure it out. Now, 2 pairs, just to give you an example of it, right? You can have maybe something like, say, a 7 of hearts. So a 7 of heart. Then you can also have, like, say, a 7 of spades, and then we also have maybe like say a 2 of diamond, and then we also have a 2 of clubs, and the last number is going to be something besides 7 and a 2, so maybe something like say a 5 of diamond then. So that would be an example of 2 pairs where 2 of the cards have the same rank, and then another 2 cards have the same rank, and the last one is a singleton. So let's try to break it into pieces so you can see how that actually works out then. So first, let's look at the first pair. Okay, so in the first pair, here's how I see it. You have in your poker card deck, you have 13 ranks, okay, and we have 4 suits. Now the suits are basically, you have your hearts, you have your diamonds, you have your clover, and then you have your clubs. And we're not looking at that, so we don't have to worry about that guy. But the one we do have to worry about is the rank. And the 13 ranks that we're talking about will be like ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Now, in each rank, what's going to happen is in order to form a pair, you're going to select 2 cards out of the 4 that's in the rank. Each rank, there are 4 cards, right? Because you have 4 of each suit. So one setup would then be the following, 4C2, because this would then give me a single pair, Now, the way it works is that we're going to form 2 pairs out of this. So that means we have to do this 4C2 2 times. So one part is going to be 4C2 and then multiply again by 4C2 because the first one is going to represent the first pair. Okay, and then the second one is going to represent the second pair. And if you can kind of go with this example right here, then we can do it for the singleton, but we're going to go ahead and leave that alone for the time being. Let me just go ahead and erase that last part just to kind of finish this part up, okay? Now, you have a first pair, you have a second pair, and the 13 rank thing, where that comes in right now is the following. If you go back to our previous example, you'll notice how in the binomial distribution there was a 4c1 and 4c2 and so forth in front of each one. Well, then in this case, it's going to be the same idea, because what's happening is you have 13 ranks and you're selecting two of the ranks in order to create the pairs. So that means in front of this, there should also be a 13c2, because the way we describe it is out of the 13 ranks, okay, you select two ranks to make the two pairs. Okay, and again, it's combination because the order doesn't matter when you get the pair, so long as you get the pair then. So the setup what I have right now, 13c2 times 4c2 times 4c2, that will allow me to look at the two pair scenario. Remember, you still have one more card that you're supposed to select, so that means that I need to have another event set up for this one. Similarly, we now go down a little bit, okay? Out of the 13 rank, we selected 2 ranks already, so that means there are 11 ranks left. And so out of the 11 ranks, right, I am going to go ahead and select one of them, so for 11c1, and from that rank, now I'm going to choose a singleton. So that is then multiplied by 4c1, okay? So this guy right here, that is because of the singleton that you're going to get to make the 4c to make the residual card. So that's like the 5 of diamonds that we have up there. So what that means is now we're going to take all of that, and then that's going to be our numerator, and then divide it by the 52c5 that we have up here. So that'll be our final answer. So the final setup is the probability of having exactly 2 pairs. Exactly 2 pairs is going to be equal to 13c2, because out of the 13 rank, you're going to select 2 of them. And then in each rank, you're going to select 2 cards, and you're going to do this twice because we need to create 2 pairs. So 4c2 times 4c2. Then we're going to now go into our last rank, last card, where there are 11 ranks left, and we're going to select one of them, so 11c1, multiplied by 4c1, because we're going to select one card in that rank then. All of that is going to be all the possible ways of getting 2 pairs, and we divide that by 52c5 because those are the total possible number of ways to have a poker hand out of 5 cards out of 52 then. So that'll be our answer. And I do believe the answer does come out to be around 10%, so it's been a while since I checked, so you can probably check it on your own. All right, so I think that'll do it. Hopefully, yeah, this was something that was beneficial to you. So thank you again for watching. I will see you next time then.